Hello, Mario! In this video we're going to be talking about circuits, electrical circuits. But first, just for a little introduction, the first thing we need to know is this little triangle, or this relationship here, where a familiar sort of triangular type shape calculation, where E, energy, equals intensity times resistance. E equals IR. I understand that E stands for energy, and this is measured in volts. I, as far as I am aware, stands for intensity, and this is measured in amps. And R is resistance, and this is measured in ohms. E equals IR is the little relationship. Now, if you want to calculate any of the quantities there, and you only need two of them to calculate the third one. So whatever one you want to calculate, you just put your finger over that one. So for instance, you want to calculate I for intensity, put your finger on I, and then it's just very simple. You need to put volts over ohms, and that'll give you amps. If you want to calculate E, put your finger on E, and you just I times R, amps times ohms. And there's only one left, R. Put your finger on that, and that's equal to volts over intensity. Now, the next thing we have to understand is there's two types of circuits with resistances, and that's where the resistances are in series, as I've shown in the top there. We've got two 10 ohm resistors there in series in that configuration there. Now when they're in series, the volts add, so the total number of volts is divided up between the two resistances based on the relationship E equals I over R. The amps, however, for a circuit where things are in series, are all the same, so they'll have the same amperage, and the ohms add together. So in our series circuit that we've got up there, for instance, we've got two 10 ohm resistors, so the total resistance is 10 plus 10 is 20 ohms. Now we've got 12 volts running through them, and the volts add. Now in this case here, as the resistances are both the same, they would each have an equal amount of volts, so the 6 volts each, as it turns out. But we can confirm this because if we've got our total, take our total intensity, or the total number of amps, which would be 12 volts, total voltage, over total resistance, 12 over 20, gives us 0.6 amps. So as we know that the amps are the same for each resistance, we've got 0.6 amps for each resistance, so then we can work out the voltage, because the voltage would just be I times R, which is the amps, 0.6, times resistance 10, which is 6 volts, which is what we worked out. So there's many ways of working these things out. So there's our series one, where we've got the two 10 ohm resistors, and we can see there that the volts would add, 6 and 6 is 12, that's all good. The amps will be the same, 0.6 and 0.6, and the ohms would add, total 10 plus 10 is 20. Now then we have our series where things are in parallel, and they have a different, slightly different sets of rules. So there we've got a 12 volt circuit, so the volts in this case would be all the same. Now the resistances, what we call the effective resistance, or in this case here, is calculated by this rule here, where 1 over the total resistance is equal to 1 over the sum of each of the individual resistances. So in this case here, the 1 over the total resistance will be equal to 1 over 10 plus 1 over 10, because we've got 2 there, which is 2 over 10, which reduces down to 1 over 5. So the total number of the total resistance would be 5 ohms. And then we can work out the total intensity, because we've got total voltage and the total resistance, 12 over 5, which is 2.4 amps. So here we got for the parallel, the volts will be the same, so there'll be 12 volts for each resistance. There the resistance would be the both 10. So to work out the ampage or the intensity, we'd put volts 12 over resistance 10, which gives us 1.2. So then, just looking at this one here, parallel, the volts are all the same, yes, they're both 12. The amps add together, 1.2 plus 1.2 gives us a 2.4, which we calculated as the total, and the resistances we worked out using the formula 1 over R total equals 1 over R1 plus 1 over R2. So that's our explanation. So let's now put our explanation to good use, and we'll have a look at a bit of a problem here. And here we have a circuit. Find the current through each resistance and the potential drop across each resistance. So we've got 240 volts, and here we've got some resistors here. Now clearly these two here are in parallel, and so they would have an effective resistance which would then be put in series with the 20 ohm one there. So for the first part of the calculation, we're just going to work out what the total resistance would be of the little parallel piece that we've got there, what the effective resistance of that would be. And that obviously I've done up the top here, R23 I think I've called it, is the resistance 2 over resistance 3, and I've probably numbered them slightly back to front, but I think you'll get the drift there. So we've got 1 over 75, which is there, plus 1 over 300. 300 is common denominator there. 75 into 300 goes 4, and 300 is 1, so that's 5 out of 300, which we can to bring that down to the lowest sort of thing there, lowest count, and that's 1 over 60. So the resistance, or the effective resistance of R23 is in fact 60 ohms. So that means that what we've got in here with this one and this one is a total resistance through the series circuit there of 20 plus 60. The 20 here and the 60 we've just determined, to gives us 80 ohms total. So the effective resistance of the whole circuit is 80 ohms. So now we can work out the intensity, the total intensity, which was obviously the energy total, or the total volts, over the total resistance or effective resistance, which is 240 volts over 80 ohms, and that gives us 3 amps. So there we have the 3 amps. Now we need to look at the individual resistances. Now we know that for a series circuit, the voltages add and the amps are the same. So we've worked out 3 amps here as the thing there. So we know that the ampage through the series circuit, remembering that we're talking about the combined sort of element that's created here with the parallel things. So when we go through that, the amps are the same. So we've got through, like just dealing with this one here, we've got the volts equals the intensity times resistance. So our volts equals the 20, which is the resistance, times the 3 amps, 60 volts there. And then going through the remainder bit, which has an effective resistance of 80 ohms, we have an effective resistance of 60 ohms, we've got V equals IR. 3 times 60 is 180 volts. And then if we check that we've got our 60 plus 180 is giving us 240 volts through the effective series circuit. Now, of course, then we have to look at the individual resistances there in the parallel circuit. Now, they all have the same voltage, and we've calculated that the voltage through that little aspect of the circuit is 180 volts. So straight away we can say that for 2 and 3 there, they both have 180 volts. We know the resistance, so we can calculate the amperage there, or the intensity. I equals 180 over 75 is 2.4, and 180 over 300 is 0.6. And just to check there, we know that in parallel circuits the amperages would add, so we get 2.4 plus 0.6 equals 3 amps. And yes, that's everything seems to be in order. So looks like someone's trying to tell me something here. We'll just get rid of them for a little while. So that brings us here to our answer here, which is just a bit of a roundup. I've put the various resistances across the top, the 20, the 300 and the 75. So the voltage 60, 180, 180, and for the 21 we've got 3 amps through that, and 0.6 through the 300 ohm one, and 2.4 amps through the 75 ohm. So it's combining the two together, remembering that we work out the effective resistance of the parallel circuit, and then it becomes a series circuit. We work through that. So a bit of a two-step process there, with a few little checks and balances as we go through, but nonetheless, there you go. Cheers.